In this video, I want to give a brief overview of what we'll be working on this week. And typically in this class, we have a couple modules we're working on. This week, it's just one. And there's a reason for it. It takes a little bit of extra time to really master it or like really feel confident with it. So today, this week's work is going to be all about stoichiometry, which is like a pretty big word. Really what we're doing with stoichiometry is we are going to be predicting how much of a product will form, or we'll be predicting how much of a reactant we need to have to make the thing that we want to make. So to do stoichiometry calculations, we need to have a few conversion factors on hand. And we're going to set these up using dimensional analysis because we spent so much time learning that in the first few weeks of the quarter that we're going to kind of lean on those skills to get through this. If you look for other resources out there, lots of really brilliant chemistry instructors have developed kind of different visual algorithms for solving stoichiometry problems. So if you find something that works better for you, please adopt that method. There's I can think of 4 off the top of my head. So I'm going to use the strategy that I think this class has best prepared you for. But again, feel free to find something that doesn't work or let me know if it's not working and I'll point you in the direction of some other resources. All right, so for stoichiometry equations, we are going to need a few things. We are going to need the molar mass of all of our reactants and products. We're also going to need a balanced chemical reaction. This balanced chemical reaction is going to essentially give us a mole ratio of how many products are formed from reactants. And we're going to use that to do mole to mole conversions. And we're going to use that molar mass to do mole to mass conversions or mass to mole. And so these stoichiometry problems will really be kind of a set usually of 2 to 3 conversion steps that use just these 2 conversion factors. But both of these conversion factors have to be kind of created by you. So the molar mass, we're going to get this from our periodic table. And balancing the chemical reaction, that's something that you're going to have to do as a first step, is to make sure that reaction that you're looking at is balanced. All right, so when do we do these? I like to think of chemistry problems as having kind of like red flags, which I know sounds dangerous, like it's going to attack you. Maybe it will. But it's kind of like what are the things that I'm looking for in the problem that are going to trigger my response that I should use my stoichiometry problem solving strategy to get to an answer. And so what you'll typically be given is a reaction and the mass or moles, the amount of one reactant per product. Okay, so if I see that, I'm going to feel like I don't have enough information, and that is when I know I need to use stoichiometry. I might have a situation where I actually are given information about 2 reactants instead, in which case I'm going to still do a stoichiometry problem, but I'll be doing a limiting reactant stoichiometry problem. Here, let's write that out. Okay, So now I'm going to give you a quick overview of the strategy. Again, the lectures have a detailed example that'll take you through this that I recommend you watch. This is just kind of like thinking about kind of how this chapter breaks down in terms of what you need to learn. So with that information, so once you kind of get used to mass to mole conversions and mole to mole conversions, which we'll build up to, then here is our strategy. Okay, so for all of these, our first step is to balance the equation. This will allow us to create mole to mole conversion factors. So that way, let's say I have H2 plus O2 forms water. I'll balance that. Let's see, I'm going to need to balance my oxygen, so I'll put a 2 there. Then I'm going to need to have 2 here. All right, balanced, check. So what I can do is I can interpret that into then conversion factors. So I'm actually going to make that a whole step. Build conversion factors. What I'm going to do for that is I am going to first create my mole to mole conversions. So for this one, it would be something like, all right, I have 2 moles of H2 equals 1 mole of oxygen equals 2 moles of water. So I can use any combination there. I can use 1 mole of oxygen equals 2 moles of water as a conversion factor. I can use 2 moles of hydrogen equals 2 moles of water as a conversion factor. The other one that I'm going to need is for mole to mass conversions. I'm going to need to find the molar mass or molar weight of all of my reactants and products. So like I would go through it and be like, all right, cool. Well, the hydrogen molar mass is going to be 2.016 grams per mole. I did that in my head. So if I'm a little bit off, sorry. The molar mass for my oxygen is going to be that 15.9999 times 2. So it's going to give me basically 32 grams per mole. And for my water, it's 2 hydrogen each at 1.008 plus our 15.999 from oxygen. So it'll be about 18 grams per mole. And so I'll use these as conversion factors where 2.016 grams equals 1 mole of hydrogen gas. All right, so once I have this, then I'm going to set up my problem. I'm going to identify my starting and my end. So let's say a problem says, all right, let's say, here's an example. If a problem says you have 1.0 grams of oxygen, how much water is produced? TO in grams. So for something like this, my start is that 1.0 grams of oxygen, and my end point is going to be some, I don't know what it is yet, mass of water. And so then I'm going to build out, I'll use dimensional analysis. And for cases where I'm going from mass to mass, like I know the mass of something and I need to predict the mass of something, I'll have 3 steps. If I'm given information as moles or I'm predicting information in moles, then it'll be 2 steps. So for, I'm just going to look at this as mass to mass because that's kind of what the example is. I'm always going to use the steps where I first convert mass into moles. So in this case, it would be, so we'll go mass into moles. For this case, it would be converting that 1.0 grams of oxygen gas into moles of oxygen. Then I'm going to convert the moles of what I know into the moles of what I want to know. So in this case, So I'm going to put a little note up above. I'm going to do this job here with the molar mass of O2 as my conversion factor. Then for this one, I'll convert that moles of O2 into water because that's what I'm interested in. So I'll use moles of water is my goal. And I'm going to use the balanced equation as my conversion factor. And remember, when we built those conversion factors, we said 1 mole of oxygen equals 2 moles of H2O. So I'll use that as my conversion factor. And then 3, lastly, I'm going to convert the moles into mass. So in this case, I would convert moles of water into mass of water. And I would use the molar mass of water to do that. And then I would be done with my problem. And so this is kind of our base strategy. So things that we can add on top of it. So kind of beyond the basics. I could do a limiting reactant problem. So if it's a limiting reactant problem, remember, I'll have information about 2 reactants. So in this case, I'll know the mass of, let's say, or the number of moles of 2 reactants. And so in this case, I'll just do 2-dimensional analysis problems. I spelled that real wrong. And the one that predicts the least amount or the smallest amount will be the correct answer, meaning that I really want to predict the least amount, right? Like I can't make more than I have reactants for. So these limiting reactant problems, it's usually easiest to just do 2-dimensional analysis problems from your 2 starting points. And maybe that's what we're saying here. So what you'll have here is you'll have 2 starting points. But you're going to try to get them into the same units, which means you have to convert everything into at least like moles of the product. And then you can compare them. And whichever one is smaller, that is going to be the amount that you make. And so then you can convert that into mass. The other kind of variant you'll see is then taking that information about the that you calculated using dimensional analysis and stoichiometry to figure out the percent yield. So the percent yield is going to always be equal to the actual amount, usually in mass, but you could do it in moles, divided by the theoretical amount. Got an end up there, times 100%. And so this theoretical amount, this is what you calculate using stoichiometry. And this actual amount is what is actually measured in the lab. We rarely get 100% yield. Like it's hard to collect everything, every single atom, right? And also side reactions happen. Like it's real hard to get 100%, unless like you accidentally did something where you like did a side reaction that created something that had more mass. And so you have a little bit of that around, and it's actually, you'll get like 120% yield. You're like, oh, what fell into my flask? So these are kind of the 2 other kind of side calculations you'll do with that. And that is what this whole week is about. This whole week is just stoichiometry, and it's your focus. So you'll use the chemical reaction skills we just learned, balancing equations, and you're going to use dimensional analysis as well to be able to help you through this set of calculations. And hopefully this is a helpful overview. Again, I recommend reading the linked pages or the linked text. And I also recommend watching the lecture. I'll walk through an example problem in detail.